Hello students, my name is Shashank Shekhar. So we have started the chapter that is electrochemistry, and today is our 19th day, or you can say 9th part more appropriately. So today is the 9th part of the chapter that is electrochemistry. So if I start look at the syllabus, so we have covered almost all of this part, and today is the last class of this electrochemistry chapter. Considering the theory, I am saying, not about the questions, we will see that later. But the story we have covered so far is that we have seen redox reaction, right? Then we have seen that this redox reaction can be done in two ways. Means since it can be reversible, so it can be tracked in two ways, the forward and the backward. And if it is occurring spontaneously, and if it is not occurring spontaneously, so two cases arise. And on the basis of that, we have two type of electrochemical cell. Okay, so which were galvanic cell, and say the second one was electrolytic cell, right? Electrolytic, not cell, electrolytic. Cell is termed for this spontaneous redox reaction only. Then we have seen that how can we calculate the EMF of this, say our galvanic cell, using the Nernst equation. And after that, we have seen the Gibbs free energy relation with this EMF of the cell. So this was our first part. So I have told this earlier also that this electrochemistry can be thought of two parts. The first one is basically about the EMF calculation, and the second one is mainly about our quantitative analysis of how this current, or what is the measures or factors that affect the flow of current. So seeing that part, we have conductance, then specific conductance or conductivity, right? Then moving to the further laws that govern this terms, where Oswald dilution law and our this Debye-Huckel-Onsager equation. After that, we have seen a very important law that is called Kohlraasch law, in which it was said that for an electrolyte, the total conductivity is equals to, and that conductivity was at infinite dilution. So the conductivity at infinite dilution, or specifically the molar conductivity at infinite dilution for electrolyte, is the sum of their individual contributions from its cationic and anionic part. So this was our Kohlraasch law. Then we move to the next type of electrochemical cell, that is electrolytic cell, in which electrolysis was carried out and a non-spontaneous redox reaction was driven with the help of current. Okay, so we have law of electrolysis governing those electrolysis. So this was the part of the electrolysis, so in which we have the Faraday's first law and the Faraday's second law of electrolysis. The first law was that the mass of the substance deposited is equals to the chemical equivalent, or electrochemical equivalent more appropriately, multiplied by current multiplied by time. So if you further move or simplify this formula, it would be M is equals to Z into I into T, where I into T can be termed as Q, or the charge. So M is equals to Z into Q. Z into Q. Q is the symbol of charge, and it is expressed in Coulomb. Okay. Now, what talking about Z? Z was equals to the atomic weight of that metal whose mass we are calculating, that is deposited on our say cathode. Okay. So it is the atomic weight of that metal divided by the valency of that metal in its cationic form, multiplied by, means these both things are by only, like it is written in this way. Suppose it is the atomic weight multiplied by valency, suppose it is represented by N, multiplied by F. Here F is 96485. Sometimes it is taken as 9650000. Only two zeros. Coulomb per mole. Why I am saying Coulomb per mole? Because it is Faraday constant. What is Faraday constant? So it was the charge that is present in 1 mole of electron, or it is the charge carried by 6.022 into 10 to the power 23 number of electrons, and it was equals to 96485, but the commonly used value of this Faraday's constant was 96500 coulomb per mole. So this was our electrolysis. Next, we have seen how can we use this electrochemical principles to conduct, or you can say set up different cells which can be used in our day-to-day life. So you must have seen cells and batteries. So if you consider what is a battery, so say these are only a combination of cells which are connected in series, and that combination is called battery. So a single cell is never termed as battery, it is always said as cell. And when we connect such type of cells in a series fashion, so there are two fashions, parallel and series. So if we connect more than one cell along a series, then we say that that combination can be termed as battery. So we have seen two types of cells. First was primary cells. We have seen two types of primary cells also. The first one was which was used often, and it basically consisted of say your NH4Cl paste and your ZnCl2, and zinc was the outer covering or the anode, and the cathode was your carbon, graphite, right? Moving on to the next cell was the mercury cell. So in which we take zinc amalgam and MnO2, and further we take this NH4Cl paste again, right? And the HGO that was present, it was acting as your so it was getting, since it was getting reduced, so it was acting as oxidizing agent. So this was our second mercury cell. So if I talk about the first one, the bigger cell, so that is used mainly in our remotes and all. And if I talk about that mercury cell, that small cell, it is mostly used in our watches, and say it is used in laser lights. You must have played with this laser lights. It was available in melas and all. So that consisted of small batteries. It is a type of circular battery, right? So the main functioning was that its output was low. It was approximately 1.35. Okay, considering it with that battery used in remote, it is 1.7. So both are in volts. Now this was about primary cell. It was rechargeable, it has a longer shelf life, and third one is that it has a lower output. Now today we will study more about this secondary cell. So we have seen a glimpse of it in the previous class. We have seen that inverters and your car batteries and all are the examples of your secondary cell. And the main characteristic of this primary secondary cell was that it is rechargeable. Rechargeable means it can be reused again and again after charging and charging. Yeah, after some time it may get less efficient. That is a different case, but we can say that it is rechargeable. So we see this application, its application in our daily life. So you must have seen inverters installed in your house to maintain the electric current in case of power cut. Then you must have seen that in the recent times we have cars that run on lithium batteries. We also see Totos. So it has a different terminology for different areas, but in our area we termed it as Totos, or you can say autos that run on battery. So that you can see running around here and there, right? So this secondary cell has a greater advantage due to its rechargeability, and its application is very wide, very wide. So this kind of revolutionary idea which has decreased the use of fuels and all. So if I talk about today's topics, so we will see the first of all what is secondary battery, what is the definition, what are its applications and all. Then we will see what is the cell reaction for a specific type of secondary battery. Then we will see the example of this secondary battery, that is nickel cadmium cell. After that we will move to something very interesting called as fuel cell. So this fuel cell was used in Apollo mission. You must have heard this mission, about this mission. Okay, so the fuel cell was used in that, and it is kind of very eco-friendly type of cell. So we'll see the structure of that cell and what cell reaction goes inside that fuel cell. Now I am just elaborating each and every cell reaction. Why? Because in exams you will get a new cell reaction and you have to think about the reaction, how the reaction is going on. So I think it would be a very good practice that if you look upon this complicated cell, like your primary cell you have seen, your mercury cell, right? Then you will now see the secondary cell and will see that how complicated the structure is. Although it is complicated, but the overall reaction is very easy to study. Just look at the cathode, search for the anode, you will get your thing. Okay, now the next few cell reaction we will also see. At last, we'll move to corrosion. You will be surprised to know that this corrosion, that is eating your iron in your home and deteriorating your condition of your vehicles and all, right? So this corrosion is a kind of spontaneous redox reaction only that is occurring due to exposure of iron to your moisture or water, right? So you will see how interesting this phenomena and how interestingly this phenomena works, this corrosion. You will see the reaction of it. So first of all, secondary battery. So here is a picture of a secondary battery. So this is a schematic diagram. We have cut a part of it so that you can look inside. What is a secondary battery look like? Yes. Okay. So if you see it, you can see it has a cathode and it has an anode. Here is your anode. Here is your cathode. So it can be charged. The same thing written here, that a secondary battery can be charged by passing current through it in opposite direction so that it can be used again. So this is a very important point. So suppose the current is flowing from X to Y, right? From X point to Y point in a secondary battery. So how it will get charged? So if we make that reaction that was going spontaneously drive in the opposite direction, in the non-spontaneous direction, then we will get the reactant back. We can get the reactants back, and that reactant will again give your spontaneous redox reaction. So you can just imagine a cycle. So whenever we apply current in the opposite direction in which it was supplying current. So I mean here that, so suppose your battery is having a flow of current from your anode to cathode. Yes, your battery has a flow of current from anode to cathode. Then you will supply current to charge this battery from cathode through anode. The electron will now move from cathode to anode, just opposite direction. So that reaction you have done to get electricity, you are reversing that reaction and getting your reactants back so that this reaction can be done again and you can get electricity again. So that it can be rechargeable. Right. Now, if you talk about a good secondary cell, so it can go a number of large discharging and charging cycle. So it is very obvious. So which secondary cell will be good? Would be good. That could go multiple times charging and discharging. This cycle can be continuous and can happen multiple times. So in that case, you will say that, okay, this battery is good enough. Okay. So you will, this is very obvious to imagine that what a good secondary cell would be. So it would be a good secondary cell if the number of charging and discharging cycle is more. Second, the most important secondary cell is the lead storage battery commonly used in automobiles and inverters. So this is the battery that you see in your inverters. So this is a diagram of how this battery looks from inside. Okay. This is the structure of secondary battery used in inverters. Now, if you see the structure here, it consists of lead anode. So the lead anode. Okay. A grid of lead packed with lead oxide. Here is the lead oxide. And as cathode, we have the lead dioxide as the cathode. So lead is acting as an anode and a grid of lead packed with lead dioxide is acting as a cathode. A 38% solution of sulfuric acid is used as an electrolyte. Means you have seen acidified water that is used in the batteries. So from time to time we do add this water. So what is this water mainly containing? So this water is mainly containing your sulfuric acid. So it is a kind of acidified water such that it can act as an electrolyte. Okay, such that it can act as an electrolyte. So you will get a more clear picture after we see this cell reaction. So the things which you have to remember for now is that this positively charged grids of PbO2 will act as your electrode. Which electrode? Cathode. And your Pb will act as anode. And the sulfuric acid is acting as an electrolyte. That's it. Means the charge will flow through this sulfuric acid. Next, cell reaction. What is the cell reaction? What does cell reaction look like in this your lead acetate battery? Lead acetate battery. So we have our Pb solid as our anode, right? So since it is present at anode, it will go oxidation. How it will go oxidation? It will lose 2 electrons. So if you move from here to here, you can see that there is loss of 2 electrons. So 2 electrons are being lost, right? So these 2 electrons are reflected here. So lead is acting as an anode and it is losing 2 electrons to become positively charged or to be oxidized. Now if I talk about this PbO2, okay, if we talk about this PbO2, it reacts with SO4 2- and 4H plus and takes up 2 electron. So initially it is +4 here. How it is +4? Suppose we consider that lead has an oxidation state of X. Oxygen, we know it very well. In general cases, we take it as -2. And we have 2 oxygens. And this overall charge should be 0. Therefore, it would give us +4. Now, SO4, PbSO4 2-, here it will be +2. So where are we going from? Where to where we are going from? We are going from +4 to +2. So here also 2 electrons are used up. Okay, 2 electrons are used up. We are getting an additional product, that is H2O, 2H2O, which is formed due to reaction of this H plus with O2. Okay, this reaction is totally balanced. We can add simply both these reactions to get our overall cell reaction. So if you add it, it would look like this Pb, this SO4 2- will add up and will be 2 H2SO4. How we will see it later. This is PbSO4, there will be 2 PbSO4. So only these 2 electrons will get cancelled. Now what are we left with? So we are left with Pb. So Pb is written here. We are left with PbO2. It is written here. Then this 2 SO4 2- and 4H plus will make up 2 moles of H2SO4. So you can just imagine it, very easy to imagine. Imagine 2 H2SO4 will have how much of H plus? 2 into 2, 4H plus, and 2 SO4 2-. These 2 are present here, so they can add and give you 2 H2SO4 in aqueous form. Then on the right side we have this PbSO4 and 2H2O. So this is our overall cell reaction that would happen inside a lead battery. Now what is happening in the opposite reaction? Okay, what is happening in the opposite reaction? Very easy to imagine. So if I write the reactions for the opposite redox reaction, so upon charging, what will happen? This 2 PbSO4 plus 2 H2O will give PbS, PbO2 and 2 H2SO4. So this would be our reaction if we charge it. So when it is supplying electricity, it will look like this. This reaction will look like this. Now if we try to charge it, the cell reaction will look like this. So both of the reaction are going simultaneously. Okay, so this is our kind of galvanic cell, and it can also act as our electrolytic cell. Is this clear? So this is our example for secondary battery. Now if I move to the next example of a secondary battery. So this is also an example of secondary battery. So this is called as nickel cadmium cell, and it is also a very important secondary cell which has longer life than the lead storage battery. So usually this lead storage batteries have shorter life, or I can say that secondary batteries have shorter storage life, but this nickel cadmium cell has a more life. But the difficulty here is that it is more expensive to manufacture. It is more expensive to manufacture. So we shall not go into the workings of this cell and electrons. We will just see how the overall reaction looks like. How the overall reaction will look like. So if you see the structure here, we have our negative plate. Okay, we have our negative plate, and we have our, this blue one is our negative plate. Okay, the yellow one is the separator. Okay, yellow one is the separator, and the white one is the positive plate. So you can see a layer of it going again and again. Okay, again a positive cell, negative cell, and a separator. Okay, so this is our structure. Now if we consider the cell reaction, overall cell reaction, so we have cadmium, which is going to CDO. What is it losing? It is losing 2 electrons, and nickel is going to your OH3 to OH2, means it is getting 1 electron. So since 2 are present, so 2 will get 2 electrons. I mean that we have 2 moles of this NiOH whole thrice, so it will take 2 electrons to go to your NiOH whole twice. So if you try to imagine it, then this negative plate, this positive plate, which is giving electrons or which is positively charged, is our cadmium. Okay, the negatively charged is our nickel, most probably, which is nickel OiOH3. So it is used in the form of hydroxides. It is also present in solid. Okay, so this is another example of nickel cadmium cell. So if I tell you, you should remember this cell reaction. This can be important, can be of significance to you. The rest of its working is not that much important, right? Because it is not in your syllabus to covered. So this is our nickel cadmium cell. Next, a very interesting type of cell is called fuel cell. So this thermal plants and all are not a very efficient method to produce electricity to use in our day-to-day life. And one more problem that comes along with this thermal plants is that they are the major source of pollution, because we know that we have to burn coals to generate heat, and that heat will boil the water, and the steam that is produced rotates our turbine. So that's our basic mechanism used in our thermal plants. But the problem is that, first of all, your coal is a non-renewable energy. It will depleting day by day, and once a day will come that this coal reserve will be over. So that's the first method. That was the first problem. The second problem is very obvious, that whenever we burn coal, we get carbon dioxide, we get carbon monoxide, which is very harmful for our ecosystem as well as our health. Right, so they are the major source of pollution. Now we know that we can convert the spontaneous redox reaction, give free energy into, or chemical energy into electrical energy. So if we conduct, or you can say put up a setup such that it's become very efficient and give us electricity very efficiently, then we can use this principle in our day-to-day life electricity needs. Okay, so we know that galvanic cells are designed to convert the energy of combustion of fuels of hydrogen, methane, methanol into electrical energy, and such a fuel is called a fuel cell. Okay, so what we are taking simply hydrogen and methane or methanol, etc., and converting it into electrical energy by combustion of this. So one of the most successful fuel cell of this is using hydrogen. We know that this oxidized form of hydrogen is water. Water is an oxidized form of hydrogen. So if we kind of use this redox reaction more sensitively and convert your hydrogen into water, then it will be a double benefit. First of all, you will get your electricity, first thing. Second thing, you will get pure water. Okay, and this both will result in an eco-friendly output in every aspect. So you can think of how much great significance this fuel cell can hold. So that can be used, and this has been used earlier also. So this had been used in providing electrical power in our Apollo space program. So you must have heard this term, Apollo space program. I mentioned in the starting of the lecture. Okay, so this fuel cell is being used earlier before this in the Apollo space program. Now if I talk about the structure of the fuel cell, so here is a typical diagram of your fuel cell, right? So very simple to imagine. So if you look at it here, so we have this anode. Okay, we have this anode, we have a cathode. Now we have water coming out from this outlet, and the species that are going oxidized and reduced are introduced from both these sides. Now if you look at this thing, we will see that hydrogen and oxygen are bubbled through the porous carbon. So both these electrodes are made up of carbon, right? And now we pressurize hydrogen from this side and oxygen from this side, and then what will happen, since this is a kind of porous substance, so this hydrogen and oxygen can get through this electrode. Now catalysts like finely divided platinum or palladium atom are incorporated in the electrode for increasing the rate of electrode reaction. So it is filled with platinum so that it can absorb your hydrogen and oxygen, yet it infused from both sides. And the electrolyte that is present here is aqueous sodium hydroxide solution. Okay, we have sodium hydroxide solution here. So if I light it again, so we have sodium hydroxide solution here, plus we have platinum. Now we are pushing or bubbling this hydrogen and oxygen from both sides, and we are having a cathode and electrode setup, and at last we are oxidizing it to get water. So let us see what is the cell reaction that goes. So the most important thing is cell reaction. So you can see very clearly here that it is benefiting us in two ways. First of all, it is giving us water, plus it is giving us electricity and no pollution, because production of, or you can say combustion of hydrogen is not done in the excess of oxygen or in the presence of heat, so it will give no pollution. Okay, so this is a very good method. Now if I look at the cell reaction, so the cell reaction goes like this. The cell reaction goes like this. So on the cathode we have oxygen, we have pushed cathodic oxygen, bubbled oxygen through the cathode side, so it will react with 2H2O, take up the 4 electron and give us 4 hydroxides. Similarly, we have pushed 2 hydrogen molecule from anode part, therefore we will get 4 OH minus from the solution, and which will give us water and 4 electron. So if you see here, this is the elemental oxygen, so it will have a oxidation state of 0. Okay, and if you look here, now the oxidation state of oxygen in the final form is minus 2, right? We have a minus 2. Here the water has minus 2, so we can think of this one. So since 2 oxygen atoms are present, therefore 4 electrons are involved, so that it can get a charge of overall minus 2 here. So 4 oxygen will get a charge of minus 2, right? So this is our reaction on the cathode side. If I talk about the reaction on the anode side, then we have hydrogen which is reacting with OH minus and going to H2. So here also it has oxygen state of 0 because it is elemental hydrogen. Then we have +1. Okay, we have +1. So we are going from 0 to +1. Now one more thing here. If you see here, we can see that here 4 electrons are involved and here also 4 electrons are involved. So you can simply add them, right? So this thing will cancel with this thing. Okay, and we will get the final reaction as 2H2 plus O2 will give us 2H2O. So what else will get cancelled? This 4OH minus will get cancelled with this, and this 2H2O will cancel this 4 and give us 2H2O, right? So overall reaction will be reaction of hydrogen with oxygen giving us water. So look how beautifully we have used our redox reaction and get our final reaction in which we are getting water as the byproduct. There is no other best output. There can be no other best output than this, that we are getting water out of producing electricity, right? So this is a very good method. Okay, now if I want to consider one more thing, that you should remember that we are using carbon electrodes in this cell reaction. So the both of the anode and cathode are made up of carbon, porous carbon, through which your hydrogen and oxygen can be bubbled in the reaction. Now the cell reaction runs continuously as long as the concentrated reactants are supplied. Fuel cell produce electricity with an efficiency of about 70% compared to thermal plants whose efficiency is 40%. Why? Because we lose lot of energy, right? We heat it, the heat dissipation occurs there. We boil it, again the heat dissipation occurs in that step, and the turbine that is getting rotated is again facing this frictional, that is air friction. So you can see that the dissipation, since it is happening in multiple steps, the possibility of energy getting dissipated is much more. So in first step you get dissipation, second step dissipation, third step dissipation of energy, and that would result in a lower output that was to be expected than the expected output, you can say, right? But if you compare it with this fuel cell, it is 70%. You can just see the dynamic difference between these two. From going to 40% to 70% is a huge success. Why? Because in science we work very harshly to increase this percentage only by 1. So to increase the efficiency by 1 also would have been a great achievement, but here we are increasing it by 30%. You can just imagine the power is almost doubling, moving to double. You're going 40 to 70, you can say that we are increasing a percentage of almost like 80% or something like that. Sorry, 30% or something, 30 to 40%. We are increasing the output. So you can say, and not only that, we are using the simple oxygen and hydrogen that is present in a huge amount in this environment. Okay, so very kind of eco-friendly this fuel cell is. And what we are obtaining is also good. We are getting a water that is free of all impurities. You do not need to conduct any reaction because we are getting it from elemental hydrogen and oxygen. Yeah, there is no electrolytes present. That should be compensated. But it is easier to add electrolytes rather than to purify it, because to purify it you will have to need energy. But to just put it in, it is easier. You just add it and it would be you can say it would be easy to consume or ready to consume. So this was our cell reaction of our fuel cell. Now the next is corrosion. So what is corrosion? So student may get confused here, that they think that corrosion only occurs with iron. It is a word that is related to iron, but I am saying here that it is not a word related to iron. Corrosion is a common word, a general word. And what does it represent? It represents the coating of the surface of metallic object with oxides or salts of the metal. So if a metal is being coated with its oxide or its salts, such that it is getting corroded, you can say corroded. So in that case we call it as corrosion. Now if I talk specifically about our iron, then the corrosion of iron is called rusting. Okay, corrosion of iron is called rusting. Other example of corrosion is tarnishing of silver. So you must have seen your in your household that women say that okay, their shininess of the silver ornaments have been reduced. Why is it so? Because they have been tarnished with time to time due to development of this, say, our salt of this silver on this silver metal. They have been the shininess has gone, or you can say reduced. So if you take it to your jewelry shop, they will just brush it off, or you can say wash it in acid, so that your thing or your rustiness can go and you can again get your shininess back. Though there also kind of electrochemistry is involved, in which you use acidic water or use acid to remove that rusting, right? We have a development of green coating on copper also, okay, bronze also. So these are some example of corrosion, and I will today talk about this rusting of iron. So I will mainly talk about this, right? We have tarnishing of silver, development of green coating on copper and bronze. Now this has a very adverse effect on our buildings. So you must have seen that these buildings and bridges, after a time, they are declared to be non-usable, or they cannot be used further. Why is it so? Because you must have seen the ships also, that this ship of Indian Defence Force have been disabled, and you have seen your flights, suppose your fighter jets also, that serve for the country for some time, and after say 10 years or 20 years of time, they are declared at non-usable. Why is that so? Because their parts have been corroded, and if we use it further, then it may result in accidents and all, right? Because all these things are mainly made up of iron, and iron is very prone to rusting, very prone to rusting. Okay, now in corrosion, what happens is that a metal is oxidized, because we know that if we are taking silver or we are taking copper, we are taking iron, that is the pure form. There the oxidation state will be 0, and you know for metal very clearly that it cannot go to its negative state, okay, negative oxidation state. So it has a tendency to lose electrons only, or it has a tendency to get oxidized only. So when they form oxides or any other salts, they lose their electrons and become goes to their oxidized state. Now corrosion of iron is very commonly known as rusting, occurs in presence of water and air. Okay, so this happens in presence of water and air. So I want to mention one more point, is that it is not always that iron will corrode and in the presence of water and air only. They can be corroded in the other metals, can be corroded in the presence of other external elements also, right? Now the chemistry of this corrosion is quite complex, but it may be considered essential as an electrochemical phenomena. So it is an electrochemical phenomena. So we'll see the complication. So what is the cell reaction that goes, not the cell reaction, you can say electrochemical reaction that goes. So here is a very good diagram that is given in NCERT, and it is very beautifully representing how the corrosion goes, right? So what is happening here? So if you see that diagram, we have iron. So if we introduce water in it, okay, if we introduce water in it, then what will happen? That this iron, there is a potential development due to this oxygen supply and all. So just we are looking at the final reaction. Suppose here is the iron. So what will happen? This iron will lose 2 electrons. So 2 such irons will lose 2 electrons and generate 4 electrons. Now this iron will go into water in the form of ions. And as it is dissolved in aqueous, so this Fe2 plus aqueous is present. Now what will happen? This Fe2 plus aqueous will take oxygen from outside, from the environment, and form your Fe2O3. That is your ferric oxide. At the same time, simultaneously, what will happen? This 4 electrons that are released, that will take this 4H plus. Okay, this will take this 4H plus, and this 4H plus is taking this 4 electron and taking the external oxygen and giving 2 moles of water. Okay, so what is happening? We are decreasing the concentration of H plus, hence we are increasing the concentration of OH minus. Right? We are increasing the concentration of OH minus. So after increasing the concentration of OH minus, what will happen? This water will get basic, and if it is getting basic, it must be getting acidic. Okay, so you get my point. So we are moving from Fe to Fe2O3. It is getting oxidized, no problem. 3 2 is 6, 2 3 is 6, plus 3 oxidation state it is gaining. But what is happening? We can see that the concentration of H plus is decreasing due to addition of water. So this water is getting basic, and this metal oxide that is formed will be acidic. So if you see the reaction, at an anode we can see that we have 2 iron present, that is reacting with you can say water to give us 2 iron 2 plus and 4 electrons, and the electrode potential is minus 0.44. So this is a very good illustration. You should look at it very minutely. Okay, now next, here is our oxidation. How many electrons are lost? Minus 4 electrons, 2 for each iron. At the same time, this O2 will go to 2H2O. It was initially 0, now it has moved to 2H2O. So 2H2O means minus 2. So how many electrons are added? 2 electrons are added. But there are 2 of oxygen, so 2 will add 4 electrons. So each of this oxygen will add 2 electrons, so total of 4 electrons will be added, and this will be formed. So we have a 4H plus 4 electrons, right? So this is our cathode and anode reaction. Now again we will add both of these reactions. So this 2Fe will be here, this O2 is here, 4 electrons and 4 electrons cancels out. Then we have this 4H plus. This 2Fe2 plus is here, and this H2O is here. So this is the overall reaction. This is our overall reaction. Now one more thing, the ferrous ion that are produced are further oxidized by atmospheric oxygen to give ferric oxide. So this ferrous iron is produced here, and I have told you earlier this ferrous iron is further reacting with O2 and giving it Fe2O3. So you must remember this point also. This is a very important point. So what is happening here, this Fe2 plus that is produced, that is further oxidized, you can say further react with oxygen to give us ferric ions in the terms of Fe2O3 dot XH2O. So some crystallized water is present, that depends upon, that is varying, okay, and with further production of hydrogen ions. So this will facilitate more hydrogen ion. So is this clear? So this is the overall reaction for corrosion. So you must think about it. Okay, so this is a very good practice to think about the reactions, the complex reactions. So once you get a clear picture of it, then you can just apply this concept in each and every cell reaction that you will get an exam. So we have seen various applications, various complicated reactions, starting from primary batteries, secondary batteries. Secondary batteries was a much complicated one, and especially your nickel cadmium. So we have not gone through the structure of that also. At last we have seen this corrosion reaction. So with this, the theory part of this electrochemistry is over. So we will come back with the question part in the later on lectures. So we'll thank you for your time. So this was for today's lecture. Thank you.